Okay, welcome to lecture here. We're continuing on chapter 11, I think, our final chapter here. All right. So last time we started talking a little bit into chapter 11, which is dealing with chemical kinetics. Remember that kinetics basically deals with, sort of how fast or slow a chemical reaction takes place. Um, again, we talked really about what is referred to as the rate expression last time. And the rate expression is a way that we could basically relate sort of what is happening, how our reactants are changing over a period of time, how our products are changing over a period of time, and sort of the average overall rate for a particular reaction. So, under the assumption of most reactions that we deal with, sort of in kinetics, like for example, this last one that we did here, we can assume that it is sort of a forward direction, a one-way street that our reactants are basically going to our products. And what that means in terms of concentrations that we would imagine is the reactants should be decreasing with time. So in order obviously to make products, we have to use up our reactants. So over a period of time, we would expect a decrease in the amount of reactants that are present, and over that same period of time, we should expect our products to be made or being made in that time period. So we should be able to see sort of an increase in the amount of products that are basically happening as we decrease the amount of reactants. And we could do that through what is sort of referred to as the rate expression, where we do take into account as well the sort of the stoichiometry involved in the reaction. So remember that if we have sort of a generic equation of AA plus BB goes to CC plus DD, we could say that the rate is equal to minus 1 over A. Remember, this part of it takes into account the stoichiometry part of it, the change in the concentration of A over the change in time, where, basically the change in the concentration of A, for example, would be obviously your final concentration of A minus your initial concentration of A. Um, Remember that since this is a reactant, it should be decreasing with time, which means technically when you do this part of it, you will get a negative number. And that's why we do have the negative here. And as we talked about last time, typically when we sort of speak about an actual average rate for the overall reaction, it usually is a positive number. And again, that's really how you get to that positive number when you do that. You could do this relationship for everybody that's there. You could do it for your other reactant as well. 1 over B, change in the concentration of B over the change in time. The rate is equal to 1 over C, the change in the concentration of C over the change in time. The difference here is when we get to C, we are dealing with a product which we would expect to increase with time. And that means that technically, when you do the change in the concentration of C in this case, and you take your final minus your initial, you will end up with a positive number. And that's why, again, we don't have the negative here. That keeps our rate being a positive value. You obviously could do the same thing for your last guy as well. Again, going to be positive too. And you could do them sort of individually like we did here. You could set them all equal to each other because this number for this reaction would be the same number. So you could basically set everybody equal to each other. And really what that allows you to do is, as we did in a few examples last time, it allows you, if you really just know really one piece of information, maybe the overall rate, the average rate, maybe how one of these guys is changing in a period of time, you can pretty much figure out how everybody in that reaction is changing over a period of time by using these relationships. And obviously, when we do something like this is basically going to end up with molarity over seconds, which again is basically telling us how the concentration is changing over a period of time. So we use this rate expression to help us sort of understand that and do these type of problems. And again, there's kind of two ways you could do it, as we sort of talked about last time. One way is to sort of do it like this, where you take 1 over the coefficient, which again basically integrates into the calculation the multimole relationship, the stoichiometry that's happening. Or alternative to that, you could just do a straight sort of stoichiometry part of the calculation, and then sort of incorporate the time aspect of it to make it more of like a rate. So you can kind of do it either way. They both should get you the same answer at the end. Um, any questions on that stuff? I think that's about what we talked about last time. Okay. So I think we did this problem obviously on the last slide. So we'll continue on and start talking about some of the factors that have an effect on the rate of a reaction. We will probably see a little bit more of some of these things along the way in this chapter. But first off, the nature of the reactants is really important. Sort of the physical state, if you will, or physical state that they are in. If we have small molecules, they tend to react faster than larger molecules. Again, small molecules can move around a lot faster, especially if we're talking about gases, for example. When we talked about gases, obviously, the smaller the molecule is, the lighter the molar mass, the higher the velocity, which means it's obviously going to be moving around a lot faster. Um, gases obviously do tend to react faster than liquids. Again, they're in constant motion. So just by that process, you would expect them to sort of come in contact with each other, sort of react a lot faster than, say, a liquid. Liquids are also very close to one another, but they don't have as much energy. And then obviously solids are just kind of sitting there. So, if you just kind of drop two solids on each other, not much is going to happen in terms of the reaction in most cases. In terms of solids, sort of the condition of it as well. If you have sort of a powdered solid, will be more reactive than a block solid. Again, it gives it sort of more surface area for reactions to take place. Certain metals are also more reactive than others. So that's kind of like the activity series of metals. So if you remember, I think we did a lab, we talked a little bit about it, where we talked about sort of single replacement reactions. And remember, an activity series really is just kind of a list of elements, usually hydrogen somewhere in there. And basically, anything that's higher on the list is more reactive than anything lower on the list. And sort of single replacement reaction would take place. Anything lower on the list is less reactive than anything higher on the list. So it really won't replace it. We also saw sort of that activity series for like non-metals and our halogens, right? So if you remember, we had this in group 7. So again, chlorine is more reactive than bromine. Bromine is more reactive than iodine. And obviously, fluorine is more reactive than chlorine. So reactivity, say in group 7, increases as you go up. So if you have sort of a single replacement reaction where you wanted to replace chlorine with bromine, it would not take place because chlorine is more reactive. But if you want to replace bromine with chlorine, that would take place because chlorine is more reactive than that. Ions are usually a lot faster in terms of reaction as well than, say, molecules. If you have ions, you most likely have a solution. And if you have a solution and you have ions, you most likely have those guys floating around in that solution ready to sort of react. So they're kind of good to go in that sense. They're ready to react. Another really important thing in terms of the rate of a reaction is temperature. That is something that could have a sort of drastic effect on a reaction. In general, if you sort of raise the temperature by about 10 degrees Celsius, a lot of times the reaction will actually double in terms of how fast it will take place. So if you just think about the idea of when you raise temperature, a lot of things do happen in that situation. When you raise temperature, pretty much everybody gains enough energy. When they gain enough energy, they actually have enough energy to get up and over the hill of the reaction that has to take place to get to the other side, and things tend to react a lot faster. The opposite of that is, if you sort of cool down a reaction. So if you take, say, a reaction flask or something like that, and then you put it on ice and then do the reaction, that typically will slow down a reaction, really for the opposite reason. As you kind of cool it down, lower the temperature, you're kind of taking away a lot of heat and energy from that reaction. Thus, you're going to find a lot less sort of reactants having the sufficient amount of energy for a reaction to take place. And we'll see sort of that mathematical relationship of that a little bit later on in this chapter, which is sometimes referred to as the Uranus equation. But part of that equation is, in order really for a reaction to take place, sort of two things has to happen. You have to sort of have a collision. So, everybody's got to kind of come in contact with each other. One thing about that is not all collisions will actually produce products. So just the act of two things sort of coming in contact with each other doesn't necessarily guarantee that you will make some products as a result of that. They do have to come in contact with each other really in sort of the right location, kind of like the active site as they hit each other. And the other really important thing is they need to come together with the right amount of energy. And as we'll see in that equation, that right amount of energy is sometimes was referred to as E of A, or the activation energy. And we'll see that a little bit later. But basically, the activation energy is the minimum amount of energy that's required for a reaction to take place. So again, just because sometimes referred to as collision theory, two things colliding, it doesn't necessarily always result in actual products being made. Other things that can kind of affect the rate of a reaction are catalysts. Catalysts are not products and they are not reactants. So these guys are really not reactants. They're not products. They actually don't get used up in a chemical reaction. Catalysts are really there for the most part to speed up the reaction. So a majority of the time when people talk about adding a catalyst to a reaction, they usually talk about it in the sense of it speeding up a reaction. There's actually, catalysts that can slow down a chemical reaction as well, which are sometimes referred to as negative catalysts. But most of the time when people sort of refer to catalysts, they are sort of referring to it in the sense of we're going to sort of speed up the chemical reaction. We oftentimes will see catalysts written in chemical reactions on top of the arrow. So, maybe it'll say something like platinum there. Maybe it'll say something like H plus, which means like an acid is being used as sort of a catalyst. And as we'll talk about towards the end of this chapter, catalysts basically can speed up a reaction by sort of finding a alternative pathway for that reaction to take place. So instead of everybody just sort of floating around trying to come in contact with each other, sometimes catalysts can sort of be an attractive center for everybody to sort of come down to sort of a central location and allow obviously the reaction to sort of occur a little quicker than it would if it was not present. There's different types of catalysts. There's homogeneous catalysts, which are just like homogeneous mixtures. They basically are in the same phase. That means whatever is reacting is in the same phase as the catalyst. So, for example, if you had a solutions that are reacting and you dumped in there some acid, that's probably also a solution as a catalyst. That obviously would be a homogeneous type catalyst. Heterogeneous means it's in different phases. So maybe you need to use some type of metal as a catalyst. So maybe that's solid and everything else is a gas or something of that nature. It would be more like a heterogeneous mixture, a heterogeneous a sort of catalyst, sort of the same thing, sort of different phases are seen. Other things that can affect the rate are the concentration. So generally, the larger the concentration of reactant molecules, the faster that you will typically have a reaction. So when we talk about concentration, again, molarity is kind of our most common one, which is moles of solute over liters of solution. And remember that really what is reacting, if we have a really large molarity or a large molarity, that would mean that the moles of solute would be relatively large. And it really is the solute in, say, a solution that is available to react and how many moles there are. And if obviously we have a large molarity, we would have a lot of those guys floating around, which means that we would expect probably that reaction to occur a lot quicker. Do you have a question, Austin? Or
Yeah, I did. So I was trying to figure out if something could be considered high concentration or not. Could we use like a density table to figure out whether or not it's kind of concentrated for its the amount of moles?
uh, so if you just wanted to kind of know what was had a higher sort of concentration, is that what you're sort of asking?
Yeah, I can give you like an example. In a research paper I was doing, someone said something about 64 milligrams of methane per liter, and
Yeah.
then I compare that to a density table, and it's like not nearly as dense as it would be at STP. So would that be considered not very concentrated?
Yeah, well, I suppose if you're trying to maybe compare a couple of things, you could get it. Remember that although concentration, we talk about sort of molarity as sort of a very common unit of concentration. You could use any sort of unit of as sort of concentration, like you said, maybe milligrams per liter or grams per liter, or whatever it may be. If you were going to compare it to something else, you would just want to try to get them both into the same units. And then, it's basically number wise, whichever one is larger would be more concentrated in that particular case. Because, even if you did say grams or whatever it was per liter, that's probably the grams of your solute, for example. And again, kind of the larger amount of solute in, say, a solution or whatever you may be dealing with, that's really what's reacting. So you even though, we may have like 1,000 milliliters of something, there's only really a certain amount of moles of actual solute, the stuff kind of floating around in there that's available to react. And the rest of it's like water or something like that. So, if you're trying to compare two things, you could get them to molarity to compare them. You could get them to kind of the same units. And again, the one that would have sort of probably the larger amount of, the solute or whatever sort of the solution that it is would probably be the more concentrated one in that sense, would probably be the best way.
Thank you.
Yep. Other questions? Okay, so in general, like I said, because really when you do have a solution, really what's floating around to react is the solute. So the larger you have, the greater chance those guys are going to come in contact with each other, and probably the faster the reaction would happen. Just in a really sort of basic sort of example of that, if you had a high concentration of solute circles, in a solution, like here, versus a much smaller concentration where maybe you just got a couple of those guys running around, there's probably a better chance that these guys would come in contact with each other a lot faster than, say, these guys swimming around and trying to find each other. So again, that larger the concentration, the higher frequency of everybody coming in contact with each other. Gases, concentration of gases does depend on the pressure of the gas. Um, and if we do have higher pressure, we typically have a higher concentration. And that as well, if you just think about it, when the pressure increases, right, typically the volume of the gas will decrease, which means, we're going to have everybody really close to each other in that sort of situation. Again, probably going to be allowing a lot more contact to happen at that situation than at maybe a lower pressure where everybody in terms of gases have a little bit more room to kind of fly around until they come in contact with each other. And again, obviously, as we talked about, the concentration of solutions really do depend on the solute that's in there. Again, that's really sort of the thing that's reacting. And remember that the solute is really just like the name of the solution, right? So if you had a sodium chloride solution, the solute would be sodium chloride. If you had, a hydrochloric acid solution, again, the solute would be hydrochloric acid. So the higher the molarity really does mean that we have a lot more of that guy dissolved in there. And again, that's ultimately what is reacting when we do any type of reaction. Okay, so we talked about rate expressions earlier. So we're going to now talk about what is referred to as the rate law, which is a little bit different than, say, the rate expression that we were looking at. The rate expression, really kind of deals with, the change in the concentration over a period of time. The rate law sort of deals with the sort of overall reaction, what's happening. And as we look here, we can write a rate law for this particular reaction, that the rate is equal to K times the concentration of X. times the concentration of B to the Y. And X and Y in this case are what are referred to as orders. So X and Y here are what are referred to as orders. And X would be the order with respect to reactant A. Y would be the order with respect to reactant B. Now, different than a lot of things that we do in chemistry, sometimes people think, well, I probably will just use my coefficients as those. And X and Y are not the coefficients in the balanced equation. They may end up being the same number, but that is not technically how you get it in a rate law. They are always found experimentally. So X and Y are always found experimentally. We could also take X and Y and add them together, and that will give you what is referred to as the overall order for a particular reaction. So if we add X and Y together, or X, Y, and Z, if you have 3 reactants, that will give you the overall order. And that's really important. A little bit later on in this chapter, we'll talk about it. Depending on the order of the reaction, there's some different sort of formulas and equations that we use depending on what's happening. So what is X and Y? Well, X and Y is sort of the proportion that is needed for each of those reactants to basically deliver sort of a specific rate for that reaction. So it's sort of like, when you make something, you got to throw so much of this guy in, so much of this guy, sort of the right proportion to really maintain a particular rate. The little k, as we talked about last time, is the rate constant. And one really important difference between, say, the rate law and the rate expression like we were dealing with earlier is if you look at the rate law here, it is only about reactants. So rate laws are only about the reactants. You don't put the products in a rate law, just the reactants are involved. So C and D will not ever really show up in a rate law. Again, it's only really about those things that are reacting. So it's those guys reacting, how they react, sort of the proportion that you need to kind of put in there to get a specific rate for this reaction to occur. And it's really all about the reactants. It really has nothing to do about products in that. So X and Y, which are the orders, they're found experimentally. So how do we sort of find those things? So what typically happens in sort of kinetics problems is you're oftentimes given sort of a table, and you're given a table of sort of experimental information. So you're oftentimes given a table of the concentration of your reactants. You're also given sort of an initial rate type value for each of those things. And usually it's a table of different experiments that have been done. And you could kind of use that table and do some calculations to figure out what the actual value of X and Y is based on the experimental information that was given to you in the problem. And once you do that, you then can typically figure out what the value of the rate constant is. So why don't we take a look at one together here, sort of a typical sort of rate law type problem. So in this particular reaction, we have F2 plus ClO2 goes to our FClO2. And this is a typical sort of kinetics type table that is given to you in these type of problems. Here you can see you have the concentration of one reactant, you have the concentration of the other reactant, and through an actual experiment, they were able to figure out what is sometimes referred to as the initial rate that happens. So if we wanted to figure out what the actual rate law is, and maybe we want to figure out what the value of the rate constant is, we could use this information to do that. So the first thing that we would want to do is really just write the generic rate law for this. So the generic rate law would be the rate is equal to K times the concentration of F2 to the X and ClO2 to the Y. So ultimately, we're going to use this table to figure out what X and Y is. And then once we do that, we'll figure out what K is at the end of it. So to do this, there's a couple of ways you could do it. If you really understand how things change and how rates change, you could just look at the table and sort of reason it out. Most people have difficulties with that. So a lot of times people will take more of a mathematical approach to do it. And I would recommend that probably. So we could use sort of this formula here where we take the rate 1 over the rate 2 is equal to k to the a to the x, b to the y, k, a to the x, and b to the y. So you may be asking, what is all this? What all this is you would typically go to this table, and you can see in this particular table, there's actually 3 entries for 3 different experiments that were done. And rate 1 and 2 does not necessarily mean you take the first and the second entry in the table. It just means that you pick 2 entries from the table. Now, when you're picking 2 entries from the table, you essentially want to do it in a way that's going to help you sort of easily solve for what you need. And to do that, when you go to the table, you want to pick 2 entries where one of the concentrations remain constant and the other varies. So you want to find 2 entries in the table where one of the reactants remains constant, the other reactant varies, or if you have 3 reactants by some chance, 2 of them remain constant and one of them varies. The purpose of that is obviously we want only one unknown, right? So if you have multiple unknowns, it makes it a little bit harder to solve for. So if we look at this table, we can find 2 entries where, again, one of them remains constant, the other one varies. So for example, if we look at 1 and 2, for example, here, we see that the concentration of F2 remains constant while the concentration of the ClO2 varies. So we'll start there. We'll take experiments 1 and 2. The other thing that's sometimes helpful when you're doing this is to look at the rates and put the larger rate up on top. And the purpose of that is it usually will give you a little bit nicer numbers, more whole numbers if you kind of do that. You don't necessarily have to, but again, it kind of gives you a little bit better whole numbers. So in this case, it looks like experiment number 2 has the larger rate. So what I'm going to do is put everything for experiment 2 up on top of my formula here. So everything in experiment 2 is going to go up on top. So we see that we have 4.8 times 10 to the minus 3, I think that says. And that's going to be equal to K times the concentration of F2, which is 0.1 to the X, times the concentration of ClO2, which is 0.04 to the Y. So everything that I just put up on top all came from the second entry here in this table. We're then going to put everything from entry number 1 on the bottom. So we got 1.2 times 10 to the minus 3 on the bottom. We have K. Concentration of F2 in experiment number 1 was 0.1. Concentration of ClO2 was 0.01. And again, everybody on top from experiment 1, experiment 2, everybody on the bottom from experiment number 1. Any questions on that so far? So now what we're going to do is the math. So if I take 4.8 times 10 to the minus 3 and I divide it by 1.2 times 10 to the minus 3, that should give me a 4 in this case. Coming to the other side, the K on top is the rate constant. The K on the bottom is also the rate constant. And since the name is called rate constant, I would assume that both of those values are the same number. Although I don't know what it is at this point, I do know it's the same, and they are going to cancel out. When I come to the next guy, the 0.1 to the X divided by 0.1 to the X, again, at this point, I do not know what X is, but that is the order with respect to F2. And I know for this particular reaction, that number is going to be the exact same, which means that this guy is going to cancel out and this guy is going to cancel out. Coming to my very last one here, if I take 0.04 divided by 0.01, that will give me 4 to the Y. That means that Y would equal 1 in this case. By the way, if you're not sure how to do that, you technically take the natural log of like 4 and take the natural log of 4 on this side and divide them, and you'll get 1. Basically, you can take the natural log of both sides and divide it out. We'll get you what you need there. Any questions on that part of the calculations so far? So what that tells us is with respect to ClO2, we know that the order is first order. We then would want to go back to our table and we want to pick 2 different entries. And in this case, what we're looking for is 2 entries where we keep, in this case, the ClO2 constant while we vary the F2. And it looks like in this case, it's going to be experiments 1 and 3 that will do that for us. The concentration F2 is 0.1 and 0.2. Concentration of ClO2 is the same in each of those. So if we look at experiments 1 and 3 and basically do the same thing, again, experiment 3 has the larger rate. So I'm going to put all those values up on top. So that's going to give me 2.4 times 10. Yeah, I think that's -3, I hope. -3 equals K times the concentration in experiment 3 for our F2, which would be 0.2 to the X and 0.01 to the Y. And again, everything on top is from experiment 3 from the table. Everything on the bottom is going to be from experiment number 1. And now we could kind of do the same thing. We got this guy when we divide it is going to equal 2. Same idea here. Don't know what K is, but it should be the same. When we divide our next guy, we will also get 2 to the X. And again, we already know that this guy is going to be the same. And if we do the same thing, again, you can take the natural log of 2 and divide it by the natural log of 2. You will see that X is equal to 1. So the order here with respect to F2 is 1. And we can now write our completed rate law, which would be that the rate is equal to K times the concentration of F2 times the concentration of ClO2. And both of those are first order. So just like most things with ones, you don't have to actually put it there. We could get the overall reaction here. So the overall reaction, overall order for this reaction would be 1 + 1, which would be second order. And that is found by adding basically the 1 from here and the 1 from here, the 2 orders here. Any questions so far on that? Okay, so just clear up some room here. 2 is equal to X. X is equal to 1. Once we now have the actual completed rate law with the orders, we actually can then go back and solve for what the value of K actually is. So we can actually come back now and solve for what this value of K is. And if we take that rate law and rearrange it, K would equal the rate divided by F2 divided by ClO2. So you may ask, where do I get those numbers from? You actually get those numbers from the table. You could choose experiments 1 number, you could choose experiment 2's number, or you could choose experiment 3's number. They all will give you the same answer. You just can't mix and match. So you can take any entry you want and actually put the numbers in. So I'm going to do it for experiment 1. But again, if you chose any of them, they should come out the same. So for experiment 1, we have a rate of 1.2 times 10 to the -3. The units are molarity over seconds, divided by the concentration there of 0.1 molar times our other concentration, which is 0.01 molar. And if we do all that good math there, looks like we get 1.2. Now, the units here, molarity on top, will cancel with one of the molarities on the bottom, and we will actually end up with 1 over molar seconds. are 1.2 m to the minus 1 s to the minus 1, whichever way you want to word that. And this would be the actual value of the rate constant for this, which sort of tells you, how fast the reaction is taking place. Also really important, as we'll see as we go through this chapter, that the units associated with the rate constant gives us an indication of what order reaction we're dealing with. So as we saw here, a second order reaction typically has these units: 1 over molar seconds, 1 over molar unit of time is the typically units associated with a second order reaction. Any question on where I got any of those numbers or did any of those numbers?
Where were you showing the second order, or where were you showing the units for the orders?
As to like what units go with what orders? Is that what you're asking? Yeah.
Yeah.
Yeah. So earlier, I think we touched upon it, and we'll see it again a little bit later on. But earlier, we saw some like 1 over seconds, for example, or reciprocal seconds. And that is usually what it goes with a first order reaction in terms of the rate constant units that are associated with it. It doesn't necessarily have to be 1 over seconds, as we'll talk about. It's really just 1 over some unit of time. And second order reactions overall, like this one would be being first order in F2 and ClO2, typically has these type of units here: 1 over molar seconds, or again, 1 over some type of molar unit of time. Basically, again, doesn't has to be seconds. What we typically see a lot of times in kinetics is seconds as that unit of time, because obviously if you run reactions, you typically are not going to sit there hours and days and stuff like that. It can be, but usually a lot of things happen in minutes, seconds, and stuff like that. So seconds are usually a very common unit of time associated with kinetics experiments, but it doesn't necessarily always has to be seconds or something like that. So those are two for now, very common units that you see associated with those type of reactions in terms of first order or second order reactions. Other questions on that?
I have a question on when you took the natural log of 4 on both sides to solve
Yeah.
for y.
Yeah.
Because when I like do it on the calculator, it's like 1.38. Is
Yeah.
that necessary? Because it's like 4 is equal to 4 to the y. So then wouldn't y just be 1 automatically?
It is. So I was just saying these numbers here are actually very simple to sort of figure out. Like it's going to be 1, but where can I'll do it here. I got some random thing. But mathematically, if you get ones that are maybe a little bit more difficult to maybe see that what the number may be, if you took, say that we had 4 is equal to 4 to the x, right? So if you take the natural log of 4 is equal to the natural log of this, what ends up happening is you end up on this side, it becomes the natural log of 4, and the x just comes down. And then basically you take the natural log of 4 on one side divided by the natural log of 4 on the other side would equal x, and that should equal 1 in that particular case, which again on your calculator would have the natural log of 4, which is 1.38, but then you would be dividing it by the natural log of 4, which should get you to 1. So that's sort of mathematically what happens when you take the natural log of the right-hand side, the x just sort of comes down, and then you could just divide the natural, whatever we get here, divided by, that, and it'll end up what you need. But you could just look at it, and obviously this one is easy to kind of see, and that typically is what will happen. Why I said earlier, a lot of times you might want to always kind of go with the larger rate on top, and because that usually will give you a lot of whole numbers sometimes that is kind of easy to determine what x and y is. If you did it the opposite way, it's perfectly fine. You just get some decimals, and sometimes that might be harder for you just to kind of visually maybe look at it and know what the answer is. So if you needed to sort of mathematically solve it, that's one way you could do it. Basically take the natural log of both sides and then divide it out. Other questions?
So based on getting the second order, we can still use any of the equations on the data table?
Yeah, so if you're asking to solve for k, is that what you're asking? To solve for the
Yeah.
Yeah. So to solve for k, you could absolutely use entry 1 like I did, or you could just choose entry 2 or entry 3, and they all should give you the exact same value pretty much. Again, you just can't mix and match. So if you choose entry 2, you got to use all the information for entry 2. If you choose entry 3, you could do that as well. Sometimes tables have 4 or 5 different entries in it, so you could technically choose any entry you want and plug it into there to solve for K. But the order you have to do it is you got to first figure out what the actual orders are, what the X and Y is, and then you could go solve for K and plug it in. Other questions? Okay. So this is a good way to sort of do these type of problems really mathematically. If you can look at things, you could do it that way, but you do have to, for exams or something like that, you have to describe why you chose that if you're not going to do it mathematically. A couple of things about rate laws, as we saw, rate laws are always determined experimentally, which really means in these type of problems, you will see a lot of sort of tables given to you in problems. The orders, the reaction is always in terms of reactants. So again, it's always about sort of the reactant concentration and how they react and how it affects a reaction. And nothing about, sort of the products. And again, the orders are not from the coefficients, although sometimes they may end up being the same. You know, is not how you actually get it. And when you're doing these type of things. So, for example, what does sort of a rate law sort of tell you? You could sort of figure out, what might happen if you did something to these concentrations. So let's just say, for example, you kept this guy constant, right? But you doubled, right? Say the concentration of the second guy. How would that affect the rate? Well, you could actually just put, kind of numbers in there, fake numbers, to kind of see what would happen. So let's just say originally the rate is equal to K, and we'll just say that the original concentration was 2 for this guy and the original concentration was 2 for this guy. So since this K is a constant, we're going to ignore it because it's always going to be multiplied by the same number. And obviously we would get the rate would equal 4. Now, if we did the same reaction and we decided, hey, we'll keep the first guy at 2 and we'll double the second guy, we could see that again, if we multiply it, the rate would end up being 8. So what we see here in this particular relationship is if we keep one guy constant but double the concentration of the other guy, because they're both first order, we will see a doubling in the rate. So that's sort of what a rate law could kind of tell you, kind of help you figure out, if you maybe adjust one of the concentrations by doubling it, tripling it, or cutting one in half or whatever it may be, you could kind of use it to figure out, what the effect would be on the rate of that particular reaction. Any questions on that? Just like, again, if we went the opposite way and we cut this guy in half, that would then become 1, and you would end up with basically 2 times 1, where the rate would go down by half, so you could really sort of use it to figure out, just by putting in very simple numbers, if you have a rate law, sort of what will happen in terms of the rate if you do something to it. If you double it, will the rate go up by 4? Those type of things. Any questions on that? Okay. So let's see here. Why don't you give this one a go? The rate equation is the rate is equal to KNO times O3. If the rate is equal to K times NO times O3. Again, the orders for each of these is 1 and 1. So the overall reaction here would be second order by adding those together. In this particular case, we're given the concentrations and we are given the rate at that particular point in time. So we do want to just solve for K. So if we do that, K would equal the rate divided by NO and our O3. So this one is not too bad. Just kind of plug and chug into here. So our rate is 6.6 times 10 to the minus 5 molar seconds, divided by our NO, which is 1 times 10 to the minus 6 molar, and our O3, which is 3 times 10 to the minus 6 molar. We know it's second order because that's basically how you figure out the overall order for a reaction, is you take the individual orders for each reactant and you add them together. So individually, each of them are first order, which means when we go to add them together, we end up with 1 + 1, which gives a second order reaction overall. And again, that's important because it's going to be really important a little bit later on as well, because it tells us sort of what type of reaction it is and what equations we should really be using a little bit later on. So that's how we sort of figure it out, is from the individual orders of the reactants. You just add them together. And again, if you had like 3 of them, you would add all 3 of them together and whatever it ends up being. So if we kind of punch this in here, we get 6.6. Make sure you use your exponent button, obviously, divided by 1 to the minus 6 and divided by 3 to the minus 6. And it looks like we end up with 2.2 times 10 to the 7 units here. Again, going to be molarities canceling, giving us our 1 over molar seconds, which again is a very common unit associated with our second order reaction. Any questions on that one there?
So if there wasn't a 1 and there was a different number in the exponent, would you use that in the equation too? Like, would it be to the second or third power?
You would. So you would have to incorporate that in, especially when you're solving for say k. So maybe one of these guys would be squared or third or something like that. You would definitely have to do that when you're doing for the k part. And obviously it would change the overall order. Say this guy was 2, the overall order then would be third order in that particular case. Other questions? So why don't we try another one here where you could kind of figure it out. And I'm just going to do a little change to it. Just give me 1 second to find what I'm going to change it to. I think we'll do that one. That should work, I think. So why don't you try this one? And we're just going to make one change to it, though. We're going to change this guy value. Let's change this guy's value to 4.4 times 10 to the minus 4. All right, so why don't you, using this table, figure out what is the rate law with the orders? What's the overall order of this reaction? And what is the value of the rate constant? So why don't you take a couple minutes, use this information, and again, this guy on the bottom, we will change to this. We'll hope it will work out right. I'm going to do it myself. So take a few minutes here and we'll come up with those 3 things: completed rate law, overall order of the reaction, and what is the value of the rate constant. Okay, so let's take a look and see. So again, here we have a table. So a good approach is kind of do it sort of the rate 1 over rate 2 and really pick 2 entries. And again, when we're picking 2 entries, we want to keep one of the reactants constant in terms of its concentration and vary the other. So experiments 1 and 2 will keep this guy constant while this guy is being varied. So we'll start with that guy. So if we take experiments 1 and 2, again, just a good rule of thumb, go with the larger rate up on top. You don't have to, but again, you get a little bit more whole numbers that way. And again, it makes it a little bit easier. You could really, as long as you keep everybody together, you can put whichever one you want on top. But usually if you go with that larger rate, it will kind of work out a little bit nicer, I guess is a way to put it. So I'm just going to put everything for experiment 1 up on top since it is the larger rate, and filling in my numbers here. And then we're going to go back and put everybody from experiment 2 on the bottom. All right, so if we do some math, we divide that out. That's going to be 2. Again, we don't know what the rate constant is at this point, but it is a constant number, so it should cancel. This is the same reaction, so we don't know what X is at this point, but again, should be the same number, so that will cancel. And if we divide out our last guy, Basically 34 divided by 17 gives us 2 to the y. Again, here you could probably very easily figure out that y in this case is going to be 1. So the order with respect to I minus is first order. Any questions on that part of the calculation there? We now can basically do the same thing. We just want to now keep our other guy constant and vary our first reactant here. So to do that, it looks like perhaps 2 and 3 will accomplish that. That will keep our I minus constant while our S2O8 2 minus varies. Again, I'm going to choose to kind of put the larger rate up there on top. So in that case, since I changed it, it is going to be the third one there. That is the larger rate. So I'm going to put all the information for our third entry in. And I'm going to put all our information for our second entry in there on the bottom. Again, if we do some dividing, that's going to be 4. Again, our k's will cancel. We do some dividing here, that should be 2 to the x. And again, this guy should cancel out. Again, you could probably easily see, again, we kind of put the larger numbers on top. So got some nice whole numbers here. X is going to equal 2 in this case. So it is actually second order with respect to our S2O8 after I changed it. Any questions on that part? So our completed rate law would be, in this case, we'll go right here. The rate is equal to K times the concentration of S2O8 2 minus squared times the concentration of I minus to the 1 would be our completed rate law. The overall order here in this particular case would then be 2 plus 1, which would give you third order in this particular example. Any questions on that so far? Now we can solve for K just like we did previously. So our K would equal, in this case, the rate divided by the concentration S2O8 2 minus, and as was the earlier question, you would need to square it here because of that, and divided by the concentration of I minus. So putting in those numbers, and again, at this point, you can choose any entry. I'm just going to kind of erase this real quick so I have somewhere to write. So I'm not going to choose that third entry since I just erased it, but we'll go with the first entry again. Doesn't really matter. So we'll go with 2.2 times 10 to the minus 4 molar seconds divided by 0.08 molar. Again, we need to square it, and 0.034 just to the first, and that is also molarity. We will end up with 2.2 to the minus 4 divided by 0.08 squared divided by 0.034 gets us 1.01. Now the units here, we have a molarity on top that will cancel a molarity on the bottom, and we do have a molarity being squared on the bottom, so it is 1 over molar squared seconds would be the units. And here you could see that this is also different units associated with a third order reaction, as opposed to a second order, which was 1 over molar seconds. This guy is 1 over molar squared seconds. Again, as we will see coming up here very shortly, those units associated with the rate constant, really important. It does sort of point you in the right direction in terms of everything. Any questions on where we got any of those numbers from? So we were talking about with the other one, what happens as, what can we do with sort of the rate law here? So for example, if we took our rate law that we just did, which was the rate is equal to K times our S2O82 minus squared times our I minus. Again, we could see what happens if we sort of play with the concentrations. So let's just say initially we had, again, just to make the numbers easy, we won't worry about K since it's a constant. It's always the same number. I'm just going to say I'm going to start with 2 molar of my first guy and 2 molar of my second guy. And that will give me 2 times 2 squared, which is 4. 4 times 2, which would be 8, would be my rate technically. Now, if I decided, hey, I want to double the concentration of this guy, and in the second one, if I doubled that first guy and kept the second one constant, that would then give me 4 molar squared times 2 molar. And that is 4 squared, which is 16. 16 times 2, which is 32, would be my rate. So what I would see here is my rate would actually go up by a factor of 4 in this case if I double my S2O82 minus. So again, you could kind of use rate laws to sort of determine what would happen. Obviously, if we cut back and we halved the original guy down to say 1 molar, that would give us basically 1 squared, which is 1. 1 times 2 is 2. And our rate would drop from 8 to 4, which is going down by a factor of 4. So again, you could kind of use these rate laws and really just basic numbers to sort of figure out, you know, what would happen if you did something to these concentrations, adjust something to these concentrations, how the rate would be sort of affected by that. Any questions on that there? Okay. So why don't you try another one here? Same deal. Let's determine the rate law with the orders and the value of the rate constant using the information in this table and see what you come up with. And the other one varies. So it does look like perhaps 1 and 2 will again accomplish that for us. In this case, it's actually going to keep the NO2 minus constant while varying our NH4 plus. The sort of generic rate law would be the rate is equal to K times the NH4 plus to the X and the NO2 minus to the Y. So using those two things, we'll do 1 and 2. Again, I'm going to go with the larger rate up there on top. So that is going to be our 32.3 times 10 to the minus 7. Don't forget the title here. So this is 10 to the minus 7 is equal to our K times our NH4, which is 0.06, and our NO2 minus, which is 0.2 to the Y. On the bottom, we'll go number 1, right, which is this guy here, also to the minus 7. Although if you miss that part, you'll still be okay for this part of the calculation. You'll get 0.02 to the X and 0.2 there to the Y. So doing a little bit of dividing here, we got 32.3 to the minus 7 divided by 10.8. That's going to give us 2.99. And as was the question, that's probably close enough to call it 3 at this point. You got your K that's going to cancel. You got this guy, which is going to give you basically 3 to the X, and these guys are going to cancel. And again, we can see that basically here, X is going to equal 1. Any questions on that? And again, if you did the sort of natural log sort of calculation, if you took basically the natural log of 2.99 divided by the natural log of 3 would equal X, you basically get 0.997, which again is at some point you probably could round it to the whole number of 1. Any questions on that part there? All right, so now that we kept our NO2 minus constant, we want to go back and vary it, and it looks like, and keep the other guy constant. So it looks like perhaps We could do 3 and 4 here. We'll do that for us. That's going to keep that guy constant and vary this guy. So if we look at 3 and 4, again, I'm going to put the larger guy up on top, which would be 4. So all of 4 will go up on top. And all of 3 will go on the bottom there. So doing a little dividing there. Maybe. Bad calculator here. Looks like we got a 2 equals, again, going to cancel. This time we kept that constant, so it'll cancel 2 to the y. Again, y here is going to equal 1. So we would get a rate law for this guy that the rate is equal to K times our NH4 plus times our NO2 minus. The overall order here of this reaction going to be 1 plus 1, which would be second order. And if we wanted to solve for K, K in this case would be the rate divided by the NH4 plus and the NO2 minus. Again, you could choose any one you want. So just to mix it up, why don't we go with number 3? We'll choose, and we'll put in our number. And this is where you would get the wrong answer if you ignored this earlier. So this should be 10 to the minus 10.8 times 10 to the minus 7 molar seconds divided by 0.2 molar and 0.0202 molar. And that will get us looks like we'll go with 2.7 times 10 to the minus 4 units here. Again, molarity canceling 1 over molar seconds, which is kind of the units we would expect for a second order reaction in this particular case. Any questions on where any numbers came from, why we chose any of those things, how to calculate the rate law, the orders, the rate constant from experimental information? Again, a very common set of calculations since, again, those orders are found experimentally. Any questions on any of that there? Okay, so we've talked about sort of how to determine the rate law, how to determine the overall order. So let's talk more specifically now about 3 different types of orders. The first one we're going to talk about is a first order reaction. And we'll talk about all this stuff here in just a second. I'm just going to scroll it up on the screen. There we go. So first order reactions are reactions where perhaps we go A to product. We could have a rate expression as a change in the concentration of A over time, again being negative as it's a reactant. We could have a rate law where the rate is equal to K times A, where A would be first order, and the overall order would also be first order in this case, where you have one reactant, like a decomposition reaction taking place. If we rearranged and solved for K and just looked at the units, these are the typical units associated with a first order reaction. So as we talked about a little bit earlier, it is 1 over seconds, our reciprocal seconds. And as I mentioned before, in reality, it doesn't really always have to be seconds as the unit of time. And as I mentioned, it is usually seconds because, again, when you do experiments, you usually don't wait forever for these reactions. And a lot of reactions occur very fast. So seconds is a very common unit. But again, you could have something that says 1 over minutes, 1 over hours, 1 over weeks, years, days, whatever it may be. Those are all also going to be first order reactions. The unit of the K will tell you that. So Sometimes when you get to certain problems in kinetics, they don't with blinking lights go, hey, this is first order. They will give you the rate constant value, and they'll give you the units associated with that. And you're expected to know, oh, I see 1/seconds or 1 over a unit of time. We're dealing with a first order reaction. So that's again why it's really important. The other reason why it's really important is because we do have what are sometimes referred to as integrated rate laws. And we have an integrated rate law that deals with basically the change in concentration and the change in time that occurs. And what we see on the bottom is actually two graphs that are associated with a first order reaction. The first one is the concentration on the Y, time on the X. And as we would expect, as the reaction starts, over time, we see a decrease happening in the concentration of our reactant. And that would make sense since we're assuming this reaction obviously is heading towards the product side. We can go through and basically take the natural log of everything here, and we get this equation here. And this is essentially the integrated rate law for a first order reaction. And this allows you to figure out, if you know a concentration, a beginning or ending concentration, you can maybe figure out how much time it takes to get there. If you know how much time and how much you started with, you can figure out how much is left over in that reaction. And that is what this equation basically is. We have the natural log of A. This first A is sort of the final concentration, equals the natural log of A naught, the little circle on the bottom. That's like your initial concentration. The K here is our rate constant. And T here is actually time, not temperature. So that is time. And that is the integrated rate law for a first order reaction. And if we take that sort of formula or equation and rearrange it and write it as the natural log of A is equal to minus KT plus the natural log of A naught. That is also the first order integrated rate law, but that is it written in the form of a straight line. That is y is equal to mx plus b. And very common in kinetic sort of problems, we do a lot of graphing, and we want to always do sort of a linear graph, and that is what this will get us. So if you look at this, on the y should go the natural log of A, which is what we see here. On the x should go time, which is what we see here. And if we graph that relationship, it should yield us a straight line, as we see here. And that is usually the more common first order graph that you see. Natural log of A on the y, t on the x, should yield you a straight line with a negative slope. And that slope is also important because graphically, the slope is equal to minus k. So you could graphically determine the slope if you had, did it in Excel or something like that. I got the equation of the straight line that you made there by taking minus the rate constant. The slope is going to be negative here, equals negative k, which means k will end up being a positive number. So typically when you figure out the value of k or the rate constant from the graph, it should be a positive number. In addition, there's also another equation that is sometimes used with this, and that is the half-life equation. So the half-life equation for a first order reaction is the half-life, T1 half, or the half-life is equal to the natural log of 2 divided by the rate constant. You will also sometimes see it written 0.693, and that's what you get when you take the natural log of 2 on your calculator. 0.693 divided by k will give you the half-life. Now, sometimes you do have to use both of these equations together. So sometimes you have everything in this first equation except for the rate constants, but they may give you the half-life, and you can use this half-life equation to figure out k. So there are a number of problems where you oftentimes have to use those two guys together. to solve for something that you're looking for. What is the half-life? It is pretty much what the name implies. It is the time it takes for half of whatever you got or started with to go away. So if you started with 10, it's the time it takes for you to end up with 5. And then if you go through another half-life, right, to 2.5, and after that, I would need a calculator. But following that pattern, divided by 2 is the time that it takes to get there. So important for first order for sure is a couple of things off of this slide. Let me just kind of highlight a couple of those things here to finish up on. The units associated with the rate constant is really important. The half-life equation here is important. The integrated rate law is important. And the graph, that's a lovely highlighting job there, is important as well. So that's the typical first order graph. This one's also good to know, but we will see a graph very much like that, but it will look a little bit different. But most of the time when people go first order, it is going to be that graph there on the right that we're talking about. Any questions on that? All right, we will lay it up there today. Gives us something to talk about on Tuesday, I suppose. We are down to 2 days after this, one more lecture and a final after that on Thursday. So we have lab today.